Okay, hello, I'm Hoin Jung of team number 13, and I'm going to present our project about Superpixel-based graph convolution network for semantic segmentation. Here are the members of our team and our labs. Let's see a quick overview of the problems we want to solve about semantic segmentation. Typically, semantic segmentation architectures have encoder-decoder structure like this, but the problem is images have to be compressed into small features by the encoder. The features are extended into the original size of the decoder, so boundary information loss occurs in this procedure. How can we solve this, preserving the boundary information? Here's the popular algorithm, Superpixel, which is clustering pixels by estimating the distances between each pixel. It's one of the traditional image segmenting methods. Superpixels also have been developed quickly, and there exists a state-of-the-art superpixel algorithm called SFCN of CFPR 2020. We will use SFCN to segment the image. However, it's not sufficient because we have no idea what is the class label of each superpixel. So we also adopt graph neural network, which is very useful to extract relational data. There exists a node classification task in GNN, so we regard each superpixel as a node of an image graph. By conducting node classification via graph convolutional network, we will train models to classify each superpixel's class. So here are our proposed methods of superpixel-based graph neural network for semantic segmentation. At first, as I mentioned, we will treat each superpixel as a node. So the color and spatial information of superpixel becomes a node feature by averaging them. Also, the adjacency relationship between superpixels become an edge of the graph. This is our architecture. Ground truth is also a graph with ground truth label. And a single graph convolutional layer may aggregate information only from its adjacent node, neighborhood node. So we use multiple layer, actually 12 layers with 256 channels to increase the receptive field. Also, some intermediate features will be used as one of the outputs to improve the performance, like this. In a single convolutional layer, we adopt Topology adaptive graph convolution network, which is very useful to capture information from different hops. Also, we are trying to make weighted node sampler to extract detailed information for sparse classes, though we exclude this in our final model because of the lack of time. And instead of using typical loss function, we made a no loss function, superpixel penalty loss, to consider the size of each superpixel. We gave more weight to the bigger pixels. We chose just one data set, UAV ID, which is very suitable for our framework. UAV ID dataset is a high-resolution task, and it requires detailed feature extraction for small objects such as car or human in this size of picture. We are planning to experiment to more datasets, especially medical datasets such as MONUSEC and OCT dataset. Our framework would be adopted on any segmentation dataset. Here are the experimental results. We just could implement UNet, and we get better results compared to UNet. And these BICENet and BANet are the specialized networks for this dataset. But we couldn't reach the state-of-the-art performance. Instead, we compared all the cases we can make by these ovulation study research. Our final method could improve the MIO score about 9 percentage points compared to the baseline. As a result, we successfully expanded the concept of image segmentation into graph, and it may be our first attempt in this field. And there is more possibility to be developed and be applied to various tasks. But we have some disadvantage in computational cost for pre-processing and performance. In the future, we will develop an end-to-end training model for our networks and invent more modules to deal with enhancing the performance. Yeah, that's it. And thank you.
Okay, any question? No question? Okay, thanks.
Yeah, thank you.